Hello, hello, hello. It is Mrs. Edwards and we are back. It is time to do math and I love it. Today we get to find derivatives of inverse trig functions. Now we know how to find derivatives of trig functions. We know the derivative of sine of x is cosine of x. The derivative of cosine of x is negative sine of x. The derivative of tangent of x is secant squared of x, and so on. Okay, but we now want to find the derivative of inverse trig functions. So first thing I need you guys to do is to just pause the video and jot down the derivatives of all 6 trig functions. Next, I'm going to show you how in the world they came up with these derivatives, but ultimately you should have them memorized. Now, that's kind of a lot, frankly, to memorize these, but on the AP exam, they expect that you have them memorized, and any of these 6 could show up. So let's go ahead and figure out how they found out that the derivative of sine inverse of x was equal to 1 over the square root of 1 minus x squared. I'm not going to prove all 6 of these. I'm just going to prove one of them because ultimately you need to have them memorized. Okay, so let's get started. The derivative of sine inverse of x. Well, let's start off with the original equation being y equals sine inverse of x, and we would like to take the derivative. Since we're assuming that we do not know the answer to the derivative of sine inverse of x, we want to rewrite this equation so that everything in the equation we know how to take the derivative of it. So I want to get rid of sine inverse. That's the main thing I don't know how to find the derivative. So to get rid of sine inverse, to undo that, I'm going to apply the sine to both sides. If I take the sine of the left-hand side, we'll have the sine of y. And if I take the sine of the right-hand side, sine inverse of x gets me back to x. Okay, so what I've accomplished right now is I have gotten rid of sine inverse of x, and the equation that is now in front of us, we know how to take the derivative of everything sitting there. We do know how to now implicitly differentiate. We know I'm going to have to use the implicit differentiation because this original equation that we're now working with, sine of y equals x, y is not all by itself on one side with everything with x on the other side. So the derivative with respect to x means that anything that is not an x is an input function. We're going to need to use the chain rule. We're going to chain on the derivative of that input function. Okay, so let's go ahead and take the derivative of both sides. If you were going to find the derivative of plain sine x, the answer would be cosine x. But because we want to find the derivative of sine y, it will be cosine y chain on the derivative of y. So y prime. So I've taken the derivative of sine y, gotten cosine y times y prime. The derivative of the right side, the derivative of x, is just 1. Okay, so I took the derivative of both sides. Now I can solve for y prime by just dividing both sides by cosine of y. So the answer to the derivative, right, y was sine inverse of x, and so y prime, the derivative is 1 over cosine of y. Okay, but it doesn't exactly look like 1 over the square root of 1 minus x squared. The reason that it doesn't look that way just yet is because our answer is in terms of y, but we would like it to be in terms of x. So we have to figure out a way that we can rewrite what we have here, 1 over cosine y, and change the y's into x's. Well, what's the only thing we have here where x's and y's are related to one another? Okay, so looking back up here, x is equal to the sine of y. So we're going to use this fact to get rid of the y here. We need to think of something that relates sine of y and cosine of y. Y is just an angle, right? We take a trig function of an angle measure. So what formula out there relates the sine of an angle and cosine of an angle? Hopefully, one of the Pythagorean identities comes to mind. The sine squared of an angle plus cosine squared of the same angle is equal to 1. Now, in our case, our angle is y. So I'm going to use, instead of thetas, I'm going to use y. So there's our Pythagorean identity. I'm going to ultimately make a substitution for cosine y. I want to get rid of cosine y and get sine y's in there because I know what sine y equals in terms of x. So let's solve for the cosine of y. To solve, we're going to begin by subtracting sine squared of y from both sides. And then to get rid of squaring, I'm going to take the square root. Okay, so the cosine of y is equal to the square root of 1 minus sine squared y. We can now replace this cosine y with all of that. We are closer to getting this to look like 1 over the square root of 1 minus x squared. Because, remember there's sine squared of y, come back right there, x is equal to the sine of y. Creating a little space here, I'm going to move that over there. If I square both sides, sine of y multiplied by sine of y is sine squared of y, and x times x is x squared. So we can replace this sine squared of y with x squared, and what do you know? The derivative of sine inverse of x is equal to 1 over the square root of 1 minus x squared. Now deriving these, it's time consuming. You don't want to have to take the derivative, you don't want to have to use Pythagorean identity and do all of this work each time. But I will say, if you want to derive all of them, you would start off by, if you have cosine inverse, well, just apply the cosine to both sides, and then you can use a Pythagorean identity to relate what you have and get it back in terms of x to find the answer to the inverse trig function. But I'm going to assume at this point now that you are going to have memorized these 6 derivatives. We would like to find the derivative with respect to x of sine inverse of x squared. Okay, so with respect to x, anything that is not plain x, we're going to need to treat like an input function. So we'll need to chain on the derivative of the input function. Before we find the derivative of sine inverse, though, we need to know this memorized formula here of the derivative of sine inverse of x. Every place we see an x, right there, that x guy right there, that's going to go right here in our function. Okay, so this x is that x squared. So simply making a substitution, whatever's sitting here goes there. Okay, so there's my x squared, but the extra step, because this was not plain x, we must chain on the derivative of the input function, that x squared. So times the derivative of x squared, which is just 2x, put all of this together, and our final answer is 2x over the square root of 1 minus x to the 4th. Danger, right? No one's going to commit the algebra atrocity. This is not 1 minus x squared. Okay, there's not 1 minus x squared multiplied by 1 minus x squared does not take me back to 1 minus x to the 4th. So we don't have 2 of a kind where we can take it out. So please be careful. That is simplified. We are done. Here we have another problem, and this time just a little bit of an application. Our variables are changing a bit. X of t represents the position function, and the position function equals tangent inverse of square root of t. We're asked a question about velocity, so we need to know the relationship between position and velocity. The derivative of a position function is a velocity, and the derivative of velocity is acceleration. So ultimately, to find the velocity at 16, we need to find the derivative of the position and then plug in 16. So v of t, in other words, the derivative with respect to t of tan inverse of square root of t. First thing I'm going to do, because we do not like root notation in calculus, is I'm going to immediately just rewrite that as t to the power of 1/2. We need to know the memorized formula for inverse, the derivative of inverse tangent, and there we have it. I listed it right up above. And then applying that formula, this x is t to the 1/2. So I'm going to replace this x with t to the 1/2. There's a little bit more to it, right? If we're taking the derivative with respect to t, anything that is not a plane t is going to be treated like an input function, like ugly. So that means we need the chain rule. So we're going to chain on the derivative of t to the 1/2. When you take the derivative of t to the 1/2, we move the exponent to the front, subtract 1 off the exponent. Just simplifying here, 1/2 to the power of 2 is just t to the first. Okay, but the derivative of t to the 1/2 is 1/2 t to the negative 1/2. We don't have times t prime because our variable is t. Okay, so anything that's not a plane t would be treated like an input function, but we do have a plane t, so we're good. Simplifying a bit more, this is really like times 1/2 times 1 over t to the 1/2, multiplying numerators times numerators, denominators times denominators. We have our derivative. Now we just need to substitute in 16, and we end up getting 1 over 136. Now they didn't give us whether this was feet or inches or miles or seconds, but this is a velocity, so it'd be a distance per time. But 1 over 136. When you're doing the problems tonight, just make sure that you first start with your memorized derivatives of inverse trig functions. And then if what is sitting here is not plane x, or like in this case, not plane t, then you will need to take whatever's sitting there and replace it here. But you will also need to chain on the derivative of what is sitting right there if it's not, in this case, plane x, or in this case, if it's not plane t. All right, give them a go.